Remember, if EF ever gets an X, propagate it back. This is kind of a funny way and a very subtle way of storing a graph as you see it and doing one thing with the graph. Transmitting all the X's in it along back arrows to any place they can get. CD. CD depends on DF. Is that true? CD depends on DF. And what else? I know it doesn't matter. And DD. So it's not no other arrow in our dependency diagram. On a 1, it goes to D. On a 1, it goes to D. On a 0, it goes to D and F. Now, D and F is X'd, so therefore CD gets X'd. Oh, this was already... So CD gets X'd. Now, is there anything in the algorithm that's going to stop us from taking this AD and going back there and trying to X it? Nothing. We're actually going to go back there and re-X this. Okay? And that is inefficient, but there's no way of avoiding it. It's not worth looking there to see if there's an X and then saying, OK, now I won't put an X in there. All right? So don't do that in your programs ever. You might as well just put the X in. It's faster than looking there to see if there's an X and asking a question. We'll analyze this complexity-wise later and show you that that doesn't affect the complexity much at all. So don't worry about that. We only got one more left, EF. EF depends on itself. So we're done. This stays indistinguishable. This stays indistinguishable. That means E and F can collapse into one state. And they should. It's like amoebas. That's the ugliest thing I ever saw. Just rewrite it. I just like the amoeba analogy. EF it's called. It's the final state. So that collapses. And then there's two other things that collapse. B and C. They're the same.
It just becomes a line state.
Oh, no, I lost it. Oh, crap. BC 0, 1. Is that it? Hold on. I don't want to lose it. There. I'm just double checking. I think that's it, right? OK. So now look at this machine that's minimized. What does it do? It's a lot easier to analyze now that it's been collapsed. You can have any symbol to start with.
It's every string that doesn't have a 1 in the second position.
Every string that doesn't have a 1 in the second position. If you have a 1 in the second position, you die. OK. That's the minimum machine for this. OK. Look at this picture. We started out with a graph that you didn't see the whole thing. Now the whole thing's up there for the most part, or at least the part of it that we needed. There was a beginning of this graph where some of these nodes were X'd. We wanted to transfer their X status to anything that they had back arrows to. And we did that as we went along. And now that we're finished, and there's no more arrows to put in this graph, we are finished looking at all the dependencies. What do we have? We have a bunch of X's that traveled all the way backwards and got all these X'd. And then we had a small piece of the graph that was disconnected from this piece, that are dependent on each other, but don't get dependent on any of the X's. And that piece of the graph represents states that were indistinguishable one from another. So this is really a graph searching problem. It's really algorithms. It's really discrete math stuff in disguise. It really has nothing to do with what looks like a dynamic programming table. So this is kind of a red herring here. This makes it look like something it isn't. I want to analyze how long this algorithm takes, then we'll stop for questions. You know that if you just describe this graph and traverse it, it has n squared edges, n squared, 2n squared edges, and it takes 2n squared time to traverse the graph. But that's not exactly what we're doing. We're using it in this format. So let's analyze the complexity of this algorithm particularly. How many boxes are here in terms of the number of states that we started with? N choose 2, about n squared over 2. And we look at each box exactly how many times? On the way down, 1 time on the way down. So that takes how many steps for each box? All you do is look at a 0 and look at a 1. So altogether it takes n squared to get through this. But there's this backtracking. Right? Doesn't that add extra stuff? Well, it does, but how much extra does it add? When you get backtracking, say from here, say this got x'd. You backtrack to the BC, you'd x that. Say that as something you backtrack. You backtrack there. Doesn't it seem like the worst thing that could happen is that you have to backtrack at every single step? And when you backtrack, you might actually go through n levels, backtracking up at every stage. That would make it n squared times n, or n cubed. You buy that the worst case could be n cubed? Well, it's pretty bad. It's pretty worst case, but that case is never going to happen. It's a very, very careless analysis. How come that never happens? How come you can never have backtracking go all the way back at every single stage for every single value?
So if you already backtracked on one cell, you never have to redo that further down.
Right, every time you backtrack, you kind of X things out, so you never ever have to X them out again. So let's ask ourselves, not from the point of view of we're starting here, we have to backtrack, how many might we have to backtrack from, but from the point of view if you're sitting back here empty, waiting for someone to send you an X. Oh, I hope I get an X. Then I'll be distinguished. You're sitting and waiting and waiting and waiting. You're sitting there. How many times is somebody going to possibly visit you? What's the worst that could happen? No, not once. You might get visited twice. Okay? Every single square that's waiting might get visited 2 more times. So it's impossible for every one of these to backtrack all the way through, because that would take n cubed steps, and some of these guys would end up getting visited more than twice. The worst that's going to happen is one of these guys is going to get visited, that every one of these guys is going to get visited twice more after it's empty. Total number of times, how many times does each square get visited? In the worst case, 3 times. So the worst this really takes is 3n squared. 3n squared over 2, actually, because it's half. So this is really an n squared algorithm. I don't know which way Heather learned originally. She mentioned she learned a different way. But a way that's often taught, which is simpler to describe than this, but that really is order n cubed in the worst case, works like this. You start out drawing the graph completely, all the circles. Not just little pieces of it, but draw all the circles and X out the final states, non-final states. And then look at all the single edges and propagate the X's. And then look at the graph again and look at all the single edges from there and propagate the X's again. What you end up doing if you do it that is you look at all the vertices n different times. So n squared vertices n different times. That really does take n cubed. And that's a really inefficient way to traverse the graph. But you got it. It's not that way.
Wasn't it? Did you draw any graphs?
Do you remember what you did?
Yeah. Remember? Show you real quick?
I sure do.
I don't know what that looks like. Basically, you just draw like a little chart where you group. You start by just grouping all of the accept states and all the non-accept states. And you sort of,
It's tricky.
This is the most complicated part. And then you just say, okay, from A, do I stay in the accept states? Do I stay in this group, or do I go out of this group? And for A, so we don't have the original graph up there anymore.